right. All right, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Jens Biele, who's come down to us from the AGU conference. He's travelled across to us from Germany, where he's at DLR. He's working on the Rosetta mission. Jens did a diploma at the Imperial College in London, and then did his PhD in experimental physics at the Open University in Berlin. He's now in a position where he is head of the team that's landing the Philae lander on the Rosetta mission. So he's going to talk to us about how that mission's going and where Philae lander has ended up. So please join me in welcoming Jens.
Thank you, Adrian, and thank you for inviting me to SETI Institute. My first time here, in fact. And it's an honor to tell you the latest results and ongoing activities around the Rosetta Lander Philae that landed on 12th of November, as you perhaps know, on this Comet Churyumov Gerasimenko. Now, I'm sure you know about the Rosetta mission. It's one of the few ESA cornerstone missions, flagship missions, I think you would call it in the US. It was invented in the 80s, beginning of 90s, after ESA and a couple of other agencies had the heli missions. So remember Giotto and Vegas, and so the idea was flybys are nice, but it's even nicer to go to a comet and stay there for a while, go very close, observe it over a long time as it develops its activity, and even to have a lander or a surface science probe, as it was called that time. And ESA fought very hard to get rid of the lander, but we somehow succeeded to have it on. It's not an ESA lander, it's a consortium lander. Consortium that consists of DLR, of CNES, of RC, and a number of other institutes and countries across Europe. And they finance it. It was not built by industry, it was all built by institutes, like you would build an instrument, basically, but it's a spacecraft in itself. Now, Rosetta has 11 orbiter instruments that are, of course, still in full swing and will do so until the end of 2015 at least, and then maybe half a year or so mission extension, currently think. It was launched in March 2004, 1 year later than expected, because we had the launch failure with the Ariane 5 1 year before, actually a few months before the nominal launch in beginning of 2003. And because of investigating what was wrong, so we missed this launch window. We had to go to an entirely new comet. Instead of 46P Virtanen to 67P Churyumov Gerasimenko. It's a bigger comet and more massive, more difficult to land on because you have a higher velocity if you come down, but that could be managed just. And Rosetta was on a very long track. It's a very traditional spacecraft, no electric propulsion, purely chemical. And although we had the biggest launch available in Europe at that time, the Ariane 5 extended, the injection was not enough to get us to the comet trajectory immediately. So we had a number of, actually 3 swing-bys, 2 to Earth, 1 at Mars. And that takes time. At least you lose at least 1 year every time. So it took full 10 years to arrive at the comet, and because the trajectory was beyond even the Jupiter orbit, the solar power was so low that we had to shut down almost all the systems except the central computer and the heating. So that was hibernation for almost 2 years when Rosetta was too far out, and it just went out of hibernation in January 20th this year. And that was also a first, because you can imagine that especially spacecraft controllers don't like to have their spacecraft sleeping for a long time. You never know what happens. You cannot find out for 2 years. And it was really a moment of suspense when the first signal arrived. Not really on time, because the onboard computer had a few reboots and lost some minutes, so it was really a suspense when finally the signal, but all was fine, no degradation, all worked perfect. Then we arrived, meaning at a short distance of only a few hundred kilometers, at the Comet in August 6. It was what you could call orbit injection, although it was a quasi-orbit, and the landing on November 12. So why do we have lander, and why did we fight so hard to have a lander at all? There are some core questions you can only address with landing science, with having a physical contact to this body. So, for example, is the dust you measure in the coma, even with in situ with Rosetta, is it modified as compared to the dust you have on the surface in the minerals or stuff there? Or the organic matter to that cause? It's modified already by the evaporation, but also by photoionization, and it's never the same as you have it on the surface. So is the surface pristine at all? I mean, we know comets always lose surface material, so they refresh their surface all the time, but it may take a while until the stuff really comes off. So is it still pristine there on the surface, or do we have to penetrate, for example, for sampling, a crust, or what was earlier called a comet mantle? And what are the volatiles embedded in the bulk material? Is it really only water and CO2? Is there maybe amorphous ice, or is there other volatiles? And most important for the biggest advantage of having a lander is that you can touch the body. Yeah? The physical properties of the material, the strength, the thermal conductivity, in depth, the thermal inertia, not only of the first micrometers but down, you have to touch the material and to probe it. So then the internal structure of the nucleus, that's in a radio tomography experiment. You can, a bistatic radar in fact, you need to have two units, one that acts as a main instrument and one transponder. And here in this case the lander acted as a transponder to have radio waves through the comet and to really probe the interior structure. Is it one block? Is it composed, or is it a rubble pile internally? We don't know while looking at the surface. And of course, especially the modelers always told us you need to have ground truth at least at one point to anchor your models to the surface, to have a ground truth for all your models you do in the coma and outwards. So here's a list of the orbiter instruments. I'm not going really through explaining all of them. It's an array of remote sensing and in situ instruments. In situ, most interesting is maybe the Rosina instrument, the mass spectrometer for ions and neutrals, and CONSAT is the second from the top. That's the bistatic radar that is also on the lander. The lander, as I said, was provided to ESA by our consortium, and was built mainly at DLR and MPS's Max Planck Institute for Solar System Research, now in Göttingen. And there are 10 instruments on it with a number of sub-instruments. It has a mass of 100 kilogram, and it's powered by primary battery and also by solar arrays that recharge a secondary battery. And it needs the orbiter as a relay for transmission of data, so it doesn't have a direct data connection to Earth. So here's a schematic view. That's a cut drawing. You see the number of instruments scattered everywhere, even in the feet, and there are a number of things like this ROMAP and this MUPUS in the foreground that can be deployed. The one is a magnetometer, usually on a boom as well. The MUPUS thing is a hammer that penetrates into the soil. There's an alpha particle X-ray spectrometer, is APXL, and prominently also in the foreground is this SD2, is a sampling and drilling device that puts samples into the internal gas, evolved gas analyzers, so mass spectrometers and gas chromatographs. Here's a side view from when the hood is taken off. So internally you have a number of system units, the batteries, the main electronic box, the evolved gas analyzers, that's Ptolemy and COSAC. You have a flywheel to stabilize the descent in the Z direction. The ADS is basically a gas tank, a cold gas system with thruster that goes upwards. And there's a number of cameras scattered around the surfaces, so you have a panoramic imaging capability, also stereo in one direction, and a number of dust sensors, magnetic field, ions, electrons, and the concert antennas again for the radio science experiment. The whole structure is carbon fiber, so it's not aluminum. And so what are the scientific goals of the instruments? First, determine the composition, so elemental, isotopic, mineralogic, and molecular of the surface material as it is, and measure its physical properties. So we have thermal sensors, electrical, mechanical, and determine the large-scale structure. That's the panoramic images, and also down-looking camera we have, particles and fields, and the internal heterogeneity from the radio science. So that bridges a gap between the orbiter remote sensing. For example, images have a resolution at best 1 meter or so, if it's true resolution we're talking about. And here we can go down to micrometers in principle. And to monitor the cometary activity, because it's a long-term lander, the idea is to follow the activity of the comet as it's approaching the sun and gets more and more active and spits out more and more gases and dust. And so here's a list of the instruments according to the scientific goals. I think I skipped that. So, discovery of the comet. As I said, it was pure coincidence that we flew to this comet after the launch delay, and it just happened to be the right place, the right time for launch in 2004. It was discovered in 1969 by Churyumov and Svetlana Gerasimenko, two Ukrainian astronomers, and both of them are still alive and were at ESOC and at DLR at the time of the landing, and quite happy about that. And this comet, we don't know really, we're not sure where it really comes from. Is it an Oort cloud comet or a Kuiper belt object? We know that it had a very close encounter with Jupiter in 1959. So that's when its perihelion dropped from 2.7 to 1.3, 1.2 AU, and it became a comet that you can really see when it's near perihelion. So it couldn't have been much earlier been detected than 1969. It had a number of names according to the list below, and finally it was settled to 67P. And that's the discovery image on a plate that Svetlana took in 1969. Yes. Here's a schematic of the Rosetta spacecraft. You see the lander in the foreground of the left image. It's attached to the orbiter, slightly inclined, and the high gain antenna in the chart to the lower right. And you see the very large solar area wings, 16-meter spans to each side. You need to get enough electrical power that far out in the sun. There are no RHUs or RTGs or ASRGs, no plutonium or whatever on the spacecraft. It's purely solar powered, and we don't have that radionuclide stuff in Europe anyway. Here's an image of the lander as attached to the orbiter during integration, just before a vibration test. And here's the planned landing scenario. So it's very simple in principle. You fly with the orbiter, not really very low, but it's a very slow motion around the comet because it's of a slow mass. So the orbiter moves with a speed of about 1 meter per second or so. So if you eject the lander to the rear, opposite to the direction of motion of the orbiter, what it does, it just falls down. That's not quite so because we cannot compensate all of the orbital velocity. You still have an arc of a Kepler ellipse when that intersects with the comet surface, but it's a pure ballistic descent. And what you have to do, you have to give the orbiter the command of separation at exactly the right time, at exactly the correct attitude to reach a point at the surface that you have selected beforehand. And that was done, and the colleagues at ESOC, at Flight Dynamics, really did a very, very good job. Nobody knew how to fly around a comet, and there was big concerns with the coma and the variation of outgassing that gives a drag force to the orbiter with its very large solar wings. So the number of uncertainties involved, and they made almost a pinpoint landing, although they were very conservative in the beginning, and okay, I come to that. So in principle, you could also use the cold gas system to push the lander down on its descent to accelerate it, and that was meant for the original target comet Virtanen that was much smaller, so the gravity was much lower. Then you would anchor at the surface, I come to that, and the orbiter would fly from this delivery trajectory to a more normal observing trajectory, ensuring also radio communications with the lander for sufficient time. We are talking about like 20 kilometers distance from the surface where all this happens. So to a bit tell the story of this year. Hibernation exit was on January 20, as said, and then there was extensive checks of the spacecraft, recommissioning of the lander and of all instruments on the lander and the orbiter. Our first activation was in March 28, and basically all was fine. No degradation, no slips, whatever. And then there were some major trajectory maneuvers to really get close to the comet. You have to see that you can determine the position of the comet from Earth by ground-based astronomy to like 10,000 kilometers. That's where you aim for. Once you get close and you can observe the comet in the onboard cameras, you make differential corrections. So you know the position much better, and you make differential orbit corrections to really aim for the center of the comet. At the same time, you have to brake to get the spacecraft really flying alongside the comet to later go into an orbit. So this was some 800 meters trajectory maneuvers and a lot of small correction maneuvers over the course of the spring and summer. And the orbit insertion was finally on 6th of August. It was, as I said, a quasi-orbit. It's around small objects. You can fly funny quasi-orbits, trajectories. We talk about trajectories. In this case, it was like a pyramid shape, so triangles on the sunlit side of the comet, so going up, going down, going to the side, going up. And this was first in a distance of 100 kilometers, then lowered to 50 kilometers, until we finally got into a bound orbit at 30 kilometers at first. And only after we arrived on the 6th of August to something like 100 kilometers, we could start observing the comet fully. Before it was just a dot, a pixel, and we had a very vague idea about its shape, which proved to be, well, not so good in the end. And we had no idea of where we wanted to land. So I discussed that last year, I think, with some people who do the landing site selection for NASA's Mars missions. They have very good maps and models and everything, and images, centimeter resolution, and they spend years to select the best landing site down here in the lab on conferences. And I told them, we do it all in 2 months. We didn't have no clue how it looks like before, and they said, okay, good luck and pray. And in fact, it was a bit hectic this summer. We had a vast amount of fresh data that needed to be processed very quickly. And imagery is one thing, but you have to pinpoint, you have to put it into a coordinate frames to make maps out of raw images. And you have to determine, for example, temperatures out of infrared measurements. That is not so easy. But the colleagues involved in the orbiter instruments, did real miracles and helped a lot, and did postponed their scientific papers to help us to select a landing site, or the best possible. So we had 5 candidates on end of August, and we down selected it to the nominal and a backup landing site on September 14th, according to, of course, a very well worked out catalog of criteria and processes. That was confirmed on October 12th after ESOC Flight Dynamics looked again into it and confirmed it could be reached with the orbiter. It wouldn't endanger the spacecraft. It would be all well. So the landing then was always thought to be on November 11th. But that was just an artificial, that happened to be this date because at exactly this date, the comet crossed 3 AU heliosync distance. So there's no meaning attached to it, but because it's a big holiday in France, it was delayed. It was just moved to the 12th, and it doesn't really matter. We could have moved. It could have landed weeks before and a month later. It doesn't really matter. Anyway, the primary battery then lasted until November 15th. And here's some images. These were the first resolved images from OSIRIS, from the narrow angle camera on board of the orbiter. It gets bigger as we're getting closer, and the first time I saw it, I really had to laugh. This duck-shaped thing was something nobody ever imagined. The Comet experts always told us, yeah, it's going to be something like a potato, and but more rather roundish, and yeah, but not this one. This was from 2,000 kilometers. This is from 50 kilometers. You can see this as we call it for simplicity, and everybody knows what's meant: the body, the neck, and the head. The neck is active. There's a lot of gas coming out and dust. And we first thought it's a binary, a contact binary, 2 bodies that stuck together, but it's not quite sure. And it now looks like this neck is caused by erosion, material just being eroded away from this area, and it's a self-sustaining process. So once you start it, it gets on and on. Then the lander, Philae, took an image, a selfie, of the of the orbiter. That's one of our cameras is just looking to the side across the one of the solar panels of Rosetta towards the comet. Of course, it was time to have a comet in the background. We have another image from 30 kilometers, basically looking the same. Here's one of the images they now somehow treated to, because the OSIRIS camera has a lot of different filters. You can kind of combine the different filter images into something like a color image that more or less looks like it would look to the human eye. So it's a bit reddish. It has a red slope in the spectrum, but otherwise it's very uniformly reflecting. So it's almost gray, a bit reddish. So how do you select a landing site on a comet you didn't know before? It's because we have solar power, we want to use it. You look for good places with a good solar illumination profile, so at least half a day daylight. You look for topology, so you don't want to land at the peak of a mountain because it's too small to, or you don't want to land at a cliff. You want on one level of scale below. You look for surface roughness, so it shouldn't be too rough because it's a three-legged lander, so it cannot handle too much too rough terrain. And ideally, you are concerned about soil mechanical strength. So there's since the 50s, before the first moon landings, I mean, you always have this fear that there's so much regolith loose dust, so soft that you sink in and you disappear. And I remember I had fierce but friendly arguments with the people that did deep impact, because they released shortly after the experiment that this comet only had up to 65 Pascal compressive strength. So good luck for the Rosetta Lander. It will sink into meters down, and yeah, you just forget it. And I think I managed to convince them that their measurement was not really constraining that good enough. And as we found out, we are rather on the opposite extreme. The surface was harder than expected. So flight dynamics is an important point. You have to be able to reach this point with the on the delivery trajectory with the orbiter. You shouldn't fly too close to some comet features while you're going down. And you must have radio visibility between the lander and the orbiter long enough to cover the important first couple of hours. You don't want to have an outage of RF while interesting things are happening. And there was also a thing that's a bit, it's a bit outdated now. We had nominal and backup trajectories because we have two mechanisms to separate the orbiter from the lander. The main mechanism is mechanical, electrical motors drive a belt that drives spindles. The spindles push the lander out away from the orbiter at a defined speed, all very nice. It's because it's three spindles, it's assured that the center of gravity is always between them, so that you don't tilt it somehow. But as with all mechanisms in spacecraft, you don't trust them. Mechanisms are always liable to fail or to get stuck. The motors have cold welding, whatever. So there's a backup system that is, we think it always works. There's a spring that is released, pushes off the lander at of course at only one defined speed. And you don't want to have, in case this backup mechanism is activated, you don't want to have to land somewhere totally in a totally different place or in a wrong attitude. So we were able, luckily, to choose a trajectory in the landing site that we could reach with the same velocities of the nominal as the backup mechanism. Well, that was a plus to make it more robust. And of course, last not least, for science operation, you want to have feasibility of the so-called first scientific sequence. That is the one powered by a primary battery, but also, and that works almost everywhere, but also LTS, long-term science feasibility, that requires enough solar power. And you wanted to have a place where you can do with a reasonable orbiter trajectory this radio science experiment, where you have to be with the orbiter on the opposite side of the comet as the lander for half an orbit at least. And taking all this together, there are not so many places left, and these places or these landing sites are actually regions because the landing uncertainty was thought to be about plus minus 500 meters, so on a 4-kilometer object. That is a significant spot. So here are the 5 first landing sites we are looking at, that were also a bit chosen because they contained interesting features, not too old material, so a little bit activity but not too much. And then we looked in detail at the, for example, at the surface roughness, at the how to reach it, how long does the descent take, how good is the illumination, and we came up with this one, site J it was called in the beginning. It's an Osiris image. That's pretty illuminated from the top, and it looks rather flat. If you look at the DTM, the terrain model I show later, you see it's not really flat, but it consists of terraces that are in itself kind of flat and have these cliffs between terraces. You can imagine as rice terraces. And that's good because although it's bad if you land on these cliffs, the probability to land on a cliff is of course much smaller than landing on any of these terraces. That's how it looks in a 3D model. We would land about in the center of that. And on the on the lower right, you see the rim of, maybe it's a crater, or let's call it depression. It was also considered once as a possible landing site, site B, but it turned out not to be as good as landing on this rather flat terrain at the side of B. So if you look at this terrain model and plot it in longitude, latitude, and calculate the difference of its surface normal angles from the nominal one, that's where the star is in the middle, you get these nice plots showing the surface normal delta angle, and the lander was built to tolerate about plus minus 30 degrees. It's it's a tripod. It has a cardanic joint, so it can adapt a little bit up to 30 degrees to the local terrain. But if it's more, then let's say it's getting difficult, and it may topple over or not anchor correctly. And we also have, of course, a very detailed mechanical model of all these mechanisms, and they also confirmed that 30 degrees is the most. And then it's a matter of probability if you hit something that is less or more than 30 degrees. Now, very briefly, how the the lander is operated. We have it's not really done at ESA. ESA is relaying commands from our landing control center in Cologne at DLR to the spacecraft, and the spacecraft then to the lander, and also relaying the telemetry, the housekeeping and science data that come down to the ESA antennas, and also sometimes as a supplement NASA DSN 70-meter dishes to first to LCC in Cologne, and this then is then routed to the ZONC, Science Operations and Navigation Center in France, in Knest-Toulouse, that who prepare the wishes of the experimenters into a form that we can translate them into commands and give them to ESA to send them up to the lander. And the ZONC also collects all the science data and processes them and distributes them to the scientists. All this is called RLGS, Rosetta Lander Ground Segment, and on top of this is the Rosetta Ground Segment that consists of the ISAC, the Science Center in Madrid, Spain, that is also doing the science planning, and the ESOC, the Real Control Center, and the navigation team in Darmstadt in Germany. That's how our little control room looks like. And I was not here. I was in the landing week at ESOC Darmstadt because ESA requires what they call a project authority, or in this case a lander authority, a person that they can grab at the control center and ask what's going on, what are you going to do and why. And because it was really day and night shifts, I shared it with Stefan Ulametz, the lander project manager. So the two of us were 1 week at Darmstadt and slept very little, I can tell you. But the main work was really done at our colleagues in Cologne, who have all the knowledge and all the detailed programming knowledge and the subsystem heritage to do the real work. So what happened? On the day, we had spent already a very stressy night before, because there were some hiccups when we switched on the lander, and you have to heat it up before we really do something serious, and that was not going so well, but was later understood. So we delayed the so-called go-no-go decision, where you really decide, are we going to separate and to land, or are we stopping everything and trying again in 2 weeks? That's the earliest you can do. We delayed the decision by 1 hour, and then we largely understood the problems. But not everything was perfect. The ADS tank, the descent system, this cold gas thruster, it's a tank with 70 bar of nitrogen. You have to open before you use it. You do it only some hours before, because you don't want to lose the gas to little leaks if you would do it weeks before. So that's a one-shot valve, a little needle that punctuates a diaphragm. It didn't work. At least it didn't show that it worked. You should expect pressure in the piping after this valve. Pressure rose from 0 to 1.5 bar, and that's not what you expected. So either the sensor was not good anymore, or it didn't really open. Still, we don't. That's not absolutely required, and we gave a go to ESA to separate us, which they did right on time on the 12th of November at 8:35 UTC. And the separation was perfect. We didn't need to have this backup device. It all worked fine. This is how it looked from the orbiter after the lander went away. That's a few shots from the OSIRIS camera. You see that the lander, even that the lander rotates. You see that the 3 legs have deployed already. They are folded up when still on the orbiter, and after a few minutes they fold down. You also see the 2 concert antennas as monopoles that stick out between the legs. And it rotates because, due to some imperfections you always have, you kick it in either direction, left or right turn. It's a bit random, but it's a very slow rotation, once every 8 minutes or so. That doesn't really matter. So right after separation, there was no data link to the lander, because you cannot. It's too close. It wouldn't work. The antennas of the orbiter look in this direction. The land antennas look also in this direction. So the orbiter has to turn 180 degrees, or at least 90, so that the 2 antenna cones overlap. And that takes a while to move the whole orbiter around, 2 hours in this case. But then the RF link, the radio link, was established a few seconds later than expected. And the lander immediately began transmitting telemetry and science data, images and data it did already acquire in the first 2 hours. For example, the Shiva, the lander camera farewell images. We have an image of the orbiter. It's a bit blurred because we were rotating and the orbiter was moving. But anyway, you saw the orbiter one last time from the lander. All the while, directly after separation, this concert ranging experiment, this radio experiment was on. So we use it as a radar during descent. Wasn't really its original science, but you could measure all the while the distance between orbiter and lander, and this gave us immediately confirmation. First, the lander is still alive because its experiment component on the lander is working, and you could follow the range according as planned. So it was on the right trajectory. Then there is a down-looking camera that took images while going down. Some other instruments measured and calibrated, and all well. The expected landing time was 15:34 UTC, plus minus, and there we argued a lot, plus minus 40 minutes The flight dynamics people at ESA are very, very conservative. They take 3 sigmas and double it and something and round it up for good measure. And in reality, it was only 6 seconds late. So, okay. And how did we see it? We saw live telemetry, of course, 28 minutes later after the one-way light travel time. So we saw a very brief link break, a flickering of the radio signal, and then, actually it was immediate, but you only get this housekeeping value every couple of minutes. We saw that the landing gear damping element, it's kind of a shock absorber, went in, so that you really touched ground. And then the anchors, these harpoons that were meant to anchor the lander, we saw that the rewind motors that pull in the tethers were engaged, and that a touchdown signal was generated. That is done by this shock absorber automatically and is submitted to the onboard computer and linked up to the orbiter. So we thought, perfect, all is fine. So as said, there was this touchdown signal. So clearly we touched on the comet, but then the radio link showed fluctuations. It went off every 40 seconds to 3 minutes for just a second and then came back immediately. And a number of sensors also showed, actually experiments, that something was not stable. Sensors measuring the temperature of the comet surface, for example, saw warm, cold, warm, cold. So that cannot be true if you're just sitting on the surface and the sun is slowly moving over the sky. Also on the solar panels that cover the whole surface of the lander, we saw that each panel saw fluctuating currents and voltages. And yeah, rather quickly we concluded we must be flying, hopping. So that caused some concern, and the party was a bit subdued until we finally said, we have good news. We didn't land just once, we landed twice. Because after 1732, we saw no more fluctuations in all the sensors, so we must have finally settled on the surface. At least the second time, as we later learned, it was maybe the third time. So the LOS, the loss of signal, when naturally the orbiter goes below the horizon of the lander, was 1759. But so half an hour or so we sat happily on the Comet and had radio link. The experiments were ongoing, and after that it was a bit unclear when we would really come back, because it was clear we didn't land where we wanted to land, and it was not yet clear where exactly are we. So all these plans worked out in detail for months and so on, and all the timelines were probably not worth it anymore. So when would we have the next radio link? And is the lander still alive then? We are pretty sure the lander is alive, or we knew it, because this concert experiment was doing its main experiment that time, because the orbiter was on the other side of the comet. So it did its radio sounding through the nucleus, and we saw that the data are coming and the lander is alive. So on the next day, we also got the first panoramic image of the lander at its final site. Yeah, I found this has some emotional value for me, because it's an artificial object. You see here one of the legs with the feet sitting on the surface of a comet. The first lander ever on the surface of a comet. But what do we see here? We still cannot really, still don't really understand what this is. Is this a wall, or is this just a little cliff to one side, because there's some open space you see in the upper images of the other cameras? Is not easy to interpret. And the first actually this panoramic should have been taken directly, immediately after the first touchdown, but due to some software glitch in the instrument, it didn't work, and it would have shown probably just a blurred image, because we knew we were flying then, and we were also rotating and much faster than anticipated. That was caused by just bouncing off and getting an induced rotation. So why did it bounce off? Because two crucial subsystems that were meant to anchor it and hold it down didn't work. I mentioned the one was this cold gas system where the tank didn't open, or even if it was open, it still didn't work, because when we switched it on finally, it didn't boot correctly. So the software it was just a dumb instrument drawing power, but not knowing what to do. But more importantly, the harpoons, the anchors didn't work. They didn't fire. We first mistook the telemetry from these rewind motors as, oh, they have fired and the motors are pulling back the tethers, but they didn't. They were pulling back the tethers as they always do when you switch them on, but the anchors were just not fired, so they just stopped. It's not quite clear why the anchors didn't work. We suspect it's a wiring problem, so it's a bit embarrassing. The flight model anchors were probably incorrectly wired from main redundant first and second bridge wire and relays, what you have. So we commanded correctly, but the wiring went to a dead end, and that is, on the one side, it's a good thing, because we can, if this is true, then everything is intact. The gunpowder is still there, and everything could work. If you just command it the other way around, we can still fire them. And it's also scientifically important, because they're not just anchors, they carry accelerometers and thermal sensors, and they penetrate up to 2.5 meters, so you can really measure a strength profile all the way down. You get temperature at a very deep point under the surface. Well, that would really be worthwhile doing. So what we of course immediately started after, to know where we are and how we are, is analysis of OSIRIS, of the spacecraft images, because some of them even show the lander just before touchdown, but also after, when it was hopping around. We even see shadows of the lander it cast on the Comet surface. We also see kind of, it's a bit hard to interpret, but something that looks like footprints, or at least surface features that were not there before landing, but were there after. Maybe it's just dust that has been perturbed and has different color or albedo, but it looks very striking. From concept ranging from this radar, we get, that's just triangulation. We got so far the best position where the lander really is. From the RF links, we can constrain the attitude of the lander, because we know how the signal, how the attitude has to be for the signal to be strong or not so strong. Then the landing gear itself, that we measure what happened to the damping mechanism. We can simulate what happened at this bouncing impact, and find out in which direction must have been bouncing off. The power on the solar generator, because we have 6 panels in different orientations, tell you, if you know where the sun is, how the lander is oriented. And ROMAP is a magnetic sensor, acts as a 3D compass, and you compare there is no dipole field on a comet, it's not like Earth, but still it has a magnetic field, and we have a similar instrument on the orbiter, and you can correlate the two. So it's pretty, over not too large distances, it's pretty well aligned, the two fields, so you can work out what the relative attitude between orbiter and lander is from the magnetic field. NUPUS TM is a thermal mapper that also shows if you're looking at the warm surface or the cold space and its variations. ROLIS is a down-looking camera that can constrain very precisely the first touchdown point, and Sesame is an experiment that is a acoustic sounding experiment, but also has kind of microphones in the soles of the feet. So they detected very precisely the instant of when the feet touched the ground, and not only that, but when they touched something soft, a little while later something hard. So that constrains the surface mechanical properties. And well, except for curiosity, why do we need to have exact localization of the lander? It's necessary to do the concert science properly to really evaluate the interior homogeneity, and operationally also to predict the solar power for the long-term science mode I come to in a little while. Here's this famous images that Osiris took. The inserts show the magnified the lander as it flew. It's time-wise, it's from lower left to upper right. Before landing, 1514, 1519, 1523. Touchdown was at 1534. And after that, there was one image at 1543 showing the lander as it bounced to its final landing site. We even have a shadow of this image. And here's the surface as it looked before and after. So upper left is before, lower left is after, and magnified on the big image to the right. So you have these three. Is it depressions? Is it just changed dust properties? We don't know yet exactly, but it somehow fits with the lander dimensions. And we even have a few images after that. I'll show you later. Here's a shape model of the comet showing the radar constraints of the final lander position. There's this yellow diamond shape and overlaid this black stripe, and somewhere in this blue stripe, and somewhere in there a lander must be. And this was one of the first analyses. The latest one is this one. You see this very small blue strip here on the left, on the lower left of the yellowish region. This is where the lander must be, constrained by radar. It's still something like plus minus 50 meters to the long axis and some 20 meters to the other direction. But still we want to know it exactly. We want to spot the lander on an orbiter image. And I hope that the images that were done in the last couple of days will lead maybe this week or next week to really verifying that we see the lander. It's a scheme with the features you see after landing. You see, yeah, it could fit. These depressions or disturbances in the surface are much bigger than the lander feet. That are only 10 centimeters in diameter, 2 to each leg. But if you slide a little bit, or if you push up dust, you can produce features like that. We also saw in one navigation camera image just after landing something that looks really like a dust plume above the first landing site, and even more so the shadow of a dust plume. So there was really something disturbed on the surface. And here's a reconstructed trajectory, how this, what happened. The red dot is the nominal landing site where we aimed for. We came up from the north, from the top, and the touchdown 1 was near to this red spot, only like 100 meters away, where the maximum uncertainty would have been 500 meters. And then we flew here to the right, over the this big crater, this B side, and then something very funny happened. At the next kink in the curve, we must have touched the ridge of this crater, but only touched slightly. Didn't really collide, otherwise we wouldn't have flown much further. We must have just touched it, so it we see that the rotation changed. You get a much stronger nutation because you got a kick to the side apparently, and the direction changed. Velocity changed a little. So it was must have been just a gliding contact. A few centimeters lower altitude, we would have crashed against this crater ridge. And then, but it was lucky in a way, because then we ended up to the where this blue line ends. About in this this is constrained by the radar determination. If we would have continued on the original path, we would have flown to the where it goes down here to the right. This is bad because this is the winter hemisphere of the comet at this moment. We don't know it because it's not lit, so it's to the shape model for images from the orbiter. It's terra incognita, and there is no light to power the solar generator, so that would have been really bad. Here's the same simulation from the side. So you can imagine we landed at the outer edge of this crater rim apparently. You also see that the lower right side of this this model looks fairly smooth, but that's not because it's smooth, because we don't know it exactly. It's a impermanent shadow. Here's a plot of the altitude and speed during these hops after how we reconstructed it. It's all very slow. It's 0.3 meters per second in speed, dropping down to 0.1, and it's not very high. It's up to 150 meters above the surface. So it was not planned for, but we can actually use all this data and this reconstruction, because we have this. We have data on the landing gear damping stroke at the first touchdown. It's meant for. And we have the sequence of the feet touching the ground, and also their orientation. So we can reconstruct exactly the mechanical situation, how we impacted first. We even know where this boulder was and so on. And together with a very good SIMPAC model of this of the lander, we can reconstruct the first bounce. Also, we know the rotation and the distances involved, and we know that the feet didn't penetrate into the soil more than a few millimeters by the onboard cameras that also at least image the feet. And we have these images of the lander imprints of the comet and the dust plume it apparently produced. So we have already done it, constrain the bouncing trajectory, but this also then constrains the mechanical properties of the surface, because all these bounces and this slight deflection tells you something about how the surface material must be to produce these changes in direction or these bounces at the given velocity. So this can be compared with this acoustic sensor data, and also with another experiment that was later done. That was the one hammering the thermal sensor. There's a kind of rod with thermal sensors into the ground. It's a recoil-free hammer system, and it's first deployed to hold it until it's really into the soil. And then it starts hammering. It started hammering. We also observed with the acoustic experiment that it hammered, because you can listen to it. It hammered for 3 hours. Because nobody knew how strong the soil is, it has an automatic system that if its depth sensor doesn't really sense that it's going in quickly enough, it increases the energy of the hammering. And it went from 1 to 2 to 3 to level 5 to its maximum, where it's almost getting a bit dangerous. And it still didn't get in more than 20 millimeters, but maybe this was just the uncertainty of the depth sensor that was recoiling and going up and down. So the conclusion is that this, at least at this final landing site, the ground is really hard. It must be compared with experiments with tests we did on Earth, at least 1 megapascal crushing strength or compressive strength, and it could be 5 or so. And that's really something like hard ice. So that was a bit unexpected. And so how are we then on the final landing site? So the lander is sure resting on the surface. It's not anchored. The harpoons are not fired, but could probably be fired in the future. The radio link was available about as predicted, so we cannot be too far off from the direction of the antenna as it was planned for at the original landing site. So it kept its axis more or less. But the illumination is very poor. We saw that the solar panels are illuminated only for 1 hour 20 minutes per day, where the Comet day at this latitude is about 6 hours per day. The rotation period is 12.5 hours. So also combined with these panoramic images I've shown you before that are a bit hard to interpret, we must be sitting behind a wall, at least to 2 sides, or in a little hole. And that means that the long-term science that relies on solar power will be difficult. If you have optimal illumination, more than 6 hours of day per day, and you don't have obstacles making shadows on the panels, we could have started this long-term science immediately after the first scientific sequence that runs on batteries. But in this case, when the primary battery was drained, lander went off as normal, as expected. But this recharging and this solar powering, that will take much longer. Because why do we expect it will come back? Because the comet is moving ever closer to the sun from about 3 AU to 1 AU perihelion in August. So we get 9 times the solar power. Also, we are slightly on southern latitudes, so we are going there from winter to summer. So the illumination situation improves with time. And I come back to that with what we think we can predict at this moment. So, but still, it was basically a success because the first scientific sequence, which is each experiment 1 shot, was basically executed. We had to reprogram a lot, and that was also a very great work of the operations team. So we did a lot of actually every experiment run once. Not all experiments delivered data as expected. For example, we have no sorry, we didn't get the sample in the. Can I have a glass of water, maybe? Thank you. So, in the end, the primary battery was almost almost as long as expected, and the last data came on the 15th of November, midnight, and it's all automatic. When the lander recognizes, or its autonomy recognizes that the battery is about to go out, it saves all data to EEPROM, so it could be transmitted later. But we were still in radio visibility, so I'll show you some slides. Yeah. So people ask, mission over. What about the long-term science? And we think it's not yet. Although it's the location is has a very limited illumination, it will improve, as I said, every day. There is no danger of overheating, what we once thought would constrain the lifetime to March maybe. And we think in April, May, the lander will boot, so it will power up itself, but we won't recognize it because there's not enough power for communications. That we expect in May or June. And the really interesting thing happens once the batteries are warm enough and there's enough surplus power to recharge the batteries, and that is expected for July to September. So then we can recharge the secondary batteries. That gives us about 100 watt-hours, and that's enough to do all experiments one after the other. And it also changes the ESA strategy with the orbiter, because it was never meant to talk with the lander that late in the mission. Also with a lot of activity, so you cannot fly so close to the Comet anymore. And what you basically do is flybys. So the whole science program, the whole trajectory planning has to be reworked a little bit. Here's a plot showing the basically the solar declination on the Comet, the seasons. So we are in we're now almost in the northern summer and rapidly going to equinox in May. 12th of May is equinox, and the southern summer peaks at 5th of September, so almost coinciding with the perihelion. That also improves illumination on the lander. So ongoing, what are we doing now except data processing and finding out what all the instruments, what's all in the data. So where is Philae exactly? Provisionally we call it site K after J. We know it within 100 meters or so from the CONSAT data, but we want to pinpoint it of course on an image. So how did it get there? This bouncing trajectory I showed you is of course always improving, and we're really puzzled about this grazing collision at about 1620, this kink in the curve I showed you. So how is the local environment determining the shadowing for the solar illumination and the RF links and the temperatures? We have to model this, and this can be then used to better predict the time of the lander wake up and to plan for that. Good, so stay tuned, and now for the first scientific results. Most of this will be shown tomorrow at AGU, so I can only give a few indications what we are mostly talking about at the moment from the very first data. So one big surprise is that the comet surface is apparently hard, at least in 2 landing sites. So the lander explored only 1, but already 2 sites, and both show something really hard, above 1 megapascal of strength, below something that looks like a dust layer that may contain volatiles still, that is about 10 to 20 centimeters deep, and that is very soft. So this hard layer, thing is, how thick is it? It's also interesting for if you think ahead. Next mission would probably be a comet sample return, and you need to want to penetrate this crust. You want to get to the really pristine material below. We cannot say yet, but we think we can estimate a lower bound by this landing mechanics, because it's we apparently didn't break the crust, so we can give it must be at least so and so many centimeters to explain these observations. And there is already people looking for explanations. Why is there a crust? When after deep impact we thought comets are made of very porous, it's still very porous, but it's not soft material. So there's thinking about arguments about hydrophobic aromatic hydrocarbons that are form aggregates when you transform amorphous ice into crystalline ice. So the crystal structure of ice extrudes these impurities, and they could form these aggregates that form something of an organic dust and silicate crust because they stick together, and that this crust would move with the crystallization front in the comet. But I don't really believe in amorphous ice on comets, and I think it would be, if it exists, it would be much lower. So lots of theories putting forward. There are experimental observations. Actually, we did in Europe in the 90s, the so-called COSY experiments, where you simulated the comet in a big vacuum chamber and illuminated dirty ice with simulated sun. And we also saw that we get consolidation. So we got cementing of dust grains with water ice that was recondensing between dust grains. Now that was, in the last years, it went a little bit out of fashion, but now apparently we have to look back into what exactly happened in these experiments. What I'm also looking forward to is will take some time, is the derivation of the thermal inertia, so of the thermal conductivity of the surface material at the centimeter scale by the MUPUS experiment, that we can derive from the curve of the daily curve of temperature we saw at the site K. And if you look at the close-up images, and also of the, well, first of the the Rolis images, it's a down-looking camera just before the first touchdown, but also at the final landing site. And there are a couple of them also in colors, because we can illuminate the surface during night with 4 different colors, LEDs. So that looks, and the panoramic images I've shown before briefly, that really looks strange. That doesn't look like a regolith surface. It looks like a cliff, a ragged cliff, and it surprisingly looks very much like the features that you see in the kilometer scale orbiter images from 50 kilometers apart. That's so it has a certain self-affinity here, that the surface, at least where it's not covered with fine dust on horizontal surfaces, these features look the same if you look at the centimeter or decimeter scale as on the kilometer scale. That's very strange. Also, we see that there's a large heterogeneity. To the one side, it looks different as to the other side. There are patches that have an albedo of 10%, so much brighter than the average albedo of 5% or so. Some patches are darker. So is there maybe ice inclusions that are brighter? We don't know yet. But a comet, after all, doesn't seem to be as simple as we thought it is. And so we are there, and we'll be back. Thanks a lot.
Jens, I'm going to do something that I've never done before. That's give somebody their mug before they've answered any questions. Because I think you need.
What is it? Is it water?
It's water. It's water.
Okay.
It's just like the water that you haven't found on the comet. But so My question is, you had the harpoons that you were going to still fire. If this material is so hard, are they guaranteed to actually penetrate that material, or what's going to happen when you fire those into this high strength
yes, they will, because they are fired with 70 meters per second velocity. They have very sharp tips, and you can fire them even in sandstone or so. They would penetrate only a bit, only like an inch or so. But they have spikes and flukes, so they would even anchor well in hard material, but they wouldn't penetrate that deep. In very soft material, they go until the tether is exhausted. That's 2.5 meters, and then if you pull them back, then they have very big flukes that then open and make the retracted surface area 20 times higher, so that should also work.
Any other questions?
I have a crazy question. Could you use any of the harpoon or whatever you have to move the probe to another part of the comet, or
Yeah, we thought about that just before we knew the batteries were almost going to end. We had the last session when we had online telemetry. There were various ideas using firing the harpoons, but then it was not yet well understood what we had to do to be sure to fire them. We operated the drill, and the drill didn't sample anything, either because it just lifted up the lander when it tried to get into the soil, because there was no holding force, or because it didn't quite reach the surface because there was a hole under it, or because it sampled something and it didn't really evolve gases when heated to 200. We don't know exactly. Anyway, but we also deployed this MUPUS instrument, this hammer, and this also pushes quite strongly against the surface when it puts this hammer down to the surface. And what we saw in the illumination of the cells before and after, the profiles looked exactly the same. So all these things didn't really move the lander. So there is an idea that maybe in at least 1 foot is somehow stuck in a ridge, so it's more or less anchored, or at least at one point it cannot be moved so easily. What we did in the end, and this was commanded, we turned the lander. Lander can be turned by 360 degrees around the body against the landing gear to orient the solar cells in a more optimal way, to get more area, more solar cell area on that direction where we saw the sun coming every day. And that was executed, but of course that moves the lander a little and the body, but it doesn't really move it away from where it is. So maybe if you shoot the harpoons, the recoil will lead to another hop. That could be interesting.
Okay. Are you saying the organics? You figured out what they are, but you can't say tonight, or they're going to say
exactly.
tomorrow?
Well, I'm not so.
Do they know what they are?
The mass spectrometers and the gas chromatographs worked, but only in sniffing mode. So they took the gases that were naturally around the gas inlets and analyzed them. We saw a lot of signal after the first touchdown, where we must have perturbed the surface, so there was a lot of gas and dust coming out, much more than in the second site. But first, I don't really know the details, and second, I think I shouldn't be speculating now in this place.
Okay. Yeah, to help us understand the challenges a little bit better, could you tell us how strong or how weak is the comet's gravity compared to Earth's gravity? What was the approximate period when you were orbiting 30 kilometers above the surface, and about how fast was the lander moving when it struck the surface?
Okay, the gravity is 10 to the minus 4 g.
10 to the minus 4.
Yeah. The orbital period at a 30-kilometer orbit is about 1 week. The orbital velocity is 1 meter per second, and the landing velocity was also 1 meter per second. And the bouncing velocity was of the order of 0.2, 0.3 meters per second. It was all very, very slow.
So, how tall is the lander? If it had landed in 20 centimeters of dust, how much of it would have gotten buried?
Only the feet. The lander is about 1 meter 20 high, including the landing gear. Its ground clearance is 20 centimeters roughly, and the feet have a height, or the soles of about 2 inches or so. But there's also tricky mechanisms that something that's called an ice screw. It looks like a drill, it's not. If you push, if the feet have contact with the ground, they push out a big screw, an ice screw that's used in alpinism as well, that would go into the surface if it's not too hard. And that was also meant for anchoring or for preventing sliding if you have a horizontal velocity. Those came apparently out, we saw it from images of the feet, a few centimeters. But that was maybe caused by the dust layer. But on the final landing site, it's possible that the lander now, at least at 1 foot, stands on the ice screw and not on the soles, because the ice screw sticks out between the foot soles.
So you were supposed to find the origin of the universe, right?
Yeah. Yeah, that's a bit
Okay.
too much.
So
Mhm.
so then you find all the organic stuff.
Mhm.
So how does that come about?
Yeah, it's very simple to generate organics on a comet. You put some ice, I think water ice, plus some CO2 or CO into vacuum, irradiate it with ultraviolet and some protons, whatever you find in the solar system, and after a little while you get lots of organics. You can do it in the laboratory in every vacuum chamber you like. What you exactly have on the comet, why it is so black, we still don't know exactly. It's rather black. A comet is blacker than coal. It has a 4% albedo that's blacker than black paint. It's only, these images of course are in a way overexposed or just exposed in a way that they have a medium gray tone. But if you would have it in your hand, it would be really black. And although it consists of silicates, materials, and some organics, and water ice, and carbon dioxide, which are white.
So what I mean is, all the organic stuff is perhaps permeating the whole universe, and then it kind of condenses onto that.
Yeah, we also have, in primitive asteroids, we also find a lot of organics and a lot of carbon. So this is a characteristics of primitive bodies in the solar system. If you, when they aggregated into the small bodies, were not further processed as in planets, you have this rather primordial material that the solar system, at least in its inner part, consisted of. And that's full of carbon and silicates and water and oxygen, and that the idea is also to find out what contribution comets made to trigger the development of life on Earth. Yeah? You know, there is this idea that when the Earth was young, there was this late this heavy bombardment, asteroids and comets impacting all the time on the Earth and delivering a lot of stuff, including water and organics, to the early Earth. And there has been a long, still ongoing dispute where all the water comes from that we find on Earth, because it's not clear that the Earth can sweat it out all by itself. So comets were once thought to bring a lot of water to the Earth's oceans, but now well, the latest fashion is after Rosetta, the orbiter instruments detected a much higher deuterium to hydrogen ratio in the coma of this comet than we have on the Earth and its oceans. That really points to not many comets can have contributed to bring water to Earth. The other comets where the data show that the composition of this water is consistent with the one we have in the Earth oceans. So I would say it's a bit open, or maybe every comet is different and everyone has a different water composition. But okay, also you have also water in primitive asteroids, and you have a lot of organics, and you can speculate if you have this early oceans, if you feed a lot of organic material into it, and these organics are really complicated stuff, and even amino acids that you can just have on even find in meteorites. If you feed enough of them into early oceans, then you have a nice soup.
Last question.
At this point, what is the level of priority for doing a drilling and getting a sample? And another question, how is the procedure going to work for the comet, for the Philae to wake up and continue its operations? Is it going to be fully charged and wake up, or can you explain those two things?
Well, maybe I reverse the order. The waking up is fully automatic. It's a bootstrap procedure. So if there's power enough, there's some hardware that will divert first energy into heating up the electronics and heating up the batteries. And if then the temperature is enough and the power is enough, the electronics will switch on itself on, so start boot the onboard computer. And then what happens, every 30 minutes the receiver of the radio system is switched on for 2 minutes, listening for signals from the orbiter. If a signal is coming, the transmitter is switched on and trying to establish a link. They have this handshake mechanism. But this requires an extra 10 watts of power. So if we just run on solar panels, that's not enough. So we have to charge the batteries to have this additional power for the transmitter. You can charge the batteries only if the batteries are warm enough, above minus 10 degrees. So otherwise you cannot put energies into the secondaries. So the lander might try to establish a link in the beginning, but the voltage collapses when the transmitters are switched on, and this will go on for a while until there is some charge in the batteries that support the switching on for a long enough time so that we can say beep. And that will hopefully then be always longer and longer. Then you can start receiving to find out what's the status, and then you can start to commanding it to do something else in the next day is coming up. Okay, so what is of course what are we going to do? The most interesting thing that we haven't really exploited yet is the analytical instruments, the mass spectrometers, the gas chromatographs, the isotopic analysis that is also done with some chemical reaction tricks, and this is, in my view, the most interesting thing that we actually built the lander for. I mean, it's all nice what we already did, but after 20 years of development and work, you would expect a little bit more. Although it's all nice and technologically very fascinating and interesting, and the first, yeah. But we really want to do an analysis of the organics. That's what we have dozens of gas chromatography columns in this instrument. We even have columns that detect chirality, so if the molecules are left or right-handed. That's interesting. Is this racemic mixture 50-50, or is there already at comets inclination of nature to go left, and as all biological molecules on Earth? And there's much more in it. Yeah? We just need the time, and we need to be able to take samples and put it. It's the sampler is putting samples into little ovens. They're then closed by a so-called tapping station. You can heat up the oven stepwise and measure the evolved gases in mass spectrometer and gas chromatograph in sequence or in parallel, adding chemicals or not. There are some ovens that have sapphire windows where you can image the sample before or after you heat it up. So you can see look at the crystalline structure. There's an infrared microscope where you can discriminate the mineralogy of the grains, so you can do a lot more, and there's a lot more in it, and really hope it will be possible to do this.
All right. Please, if you've got any more questions, then feel free to come up to drain Jens's power just a little bit more. Please join me in thanking Jens for his great talk.